E tá ao vivo? Ok, estamos ao vivo. We're live now.
Okay.
So, pessoal, boa tarde. Boa tarde a todos que estão aqui acompanhando a gente. Nós vamos começar mais um capítulo aqui do ciclo de palestras do PPGG. E hoje o nosso convidado é o professor Neil Mitchell, da Universidade de Manchester, dos Estados Unidos, e ele vai falar para a gente hoje um pouquinho sobre o Mar Vermelho e uma possível analogia entre o Mar Vermelho e o Atlântico Sul. O professor Neil é professor de Manchester, trabalha na área de Geologia e Geofísica Marinha, principalmente com informações topográficas do assoalho oceânico. So, eu vou falar um pouquinho em inglês agora. So, Neil, thank you for accepting our invitation to give this talk. And we're all excited to hear what you have to say. So, be my guest.
Okay, thank you for inviting me. It's a pleasure to come and talk. I'll share my screen then.
Yes.
Yeah. I'll come back. Try to find.
Just a minute.
Okay.
Neil, I'm gonna talk about the questions. Pessoal, quem tiver perguntas, escrevam as perguntas aí nos comentários. E aí pode ser em inglês, pode ser em português, a gente tenta traduzir aqui para o Neil, e ele responde no final. Só lembrando que esse ciclo de palestras nosso não tem emissão de nenhum tipo de certificado, tá? Obrigado. Ok, now it's with you.
Okay, thank you. Yes, sadly my Portuguese isn't very good, but I hope you'll understand this anyway. Yeah, so thank you very much for inviting me to give a seminar with you in your lockdown series. I'd like to talk about the Red Sea. The Red Sea has been thought in the past to be a very interesting basin. It's possibly the ideal basin that's illustrating the transition from breakup of a continent and formation of a new ocean. And it's also been considered as potentially a good analogue for the early South Atlantic, in particular the evolution of the evaporite basins. We'll look at that in a minute. So what I wish to do is go through that background, motivations, why you might be interested in the Red Sea. We'll look at the crustal type. This is still debated, unfortunately not fully resolved. I'm going to bring in some work of two of my PhD students, Wen Shi, who here, this is us in front of the museum in the University of Manchester. Wen has just gone back to China to take up a government job. And Oki, who has joined us the last year, has also been doing some really, really good work. After dealing with that, we'll move on to looking at the flowage in the Red Sea and then the Red Sea seismicity. I think I'll see if I can make this screen larger and maybe give myself a different pointer, maybe an arrow. Okay. So just to introduce Manchester, in case you're not familiar with the university, it's in the UK. We call ourselves the largest university, largest single campus university. The University of London is actually larger, but it's split up into smaller colleges that work independently. So we say we're the largest, have a large number of students and staff. We have in the past had a lot of Nobel Prize winners, four of which are still on the staff. We have quite a large petroleum geology group. And the department does a lot of other work: planetary science, environment, atmospheric science, environmental biology, and so on. Quite a wide, very broad environment. So the Red Sea, if you see Arabia and Africa in satellite images, you'll probably be struck by the Red Sea. It's like a giant gash in the continent. It's over 1,000 kilometers long. It's extremely prominent. And it has attracted people over the years. It can be difficult getting permission to work here, so there hasn't been as much work done as you might expect from the interest in it. We know that the Red Sea is floored by oceanic crust along its southern part in the center here, and in parts in the central Red Sea it's also floored by oceanic crust, because we see basalts at the seabed and we dredge them, and there are some clear seafloor spreading anomalies. But elsewhere we don't know so well, so because it's all covered in thick evaporites. So the north, for example, has been thought of as stretched continental crust, not oceanic crust. So there's some really good work done by Jim Cochran on that. But other people have questioned that recently, so that's why I've put this question mark. The southern Red Sea, go back. There's still questions over what underlies the flanks of the Red Sea. Some people believe it's oceanic and others think it's continental. So I'm going to focus here on the central Red Sea, where we've put most of our effort. Here it's very slow spreading, 12 kilometers per million years. It has been, well, let me explain in a moment what we think is there. So in general, why geodynamicists, people interested in the behavior of the Earth when it under plate tectonics, why they're interested in places like the Red Sea is illustrated here. This is a numerical model produced for Seychelles India margin, so not the Red Sea, but it illustrates some of the processes we might be interested in. So with extension of the plate, you expect the lithosphere to get thinned, and as the mantle is lifted up, it loses pressure, decompresses, and that produces melting, and ultimately we get the new oceanic crust forming. So you might be interested in the Red Sea because it will illustrate this process. If we have the right data, we can quantify this whole stage through to seafloor spreading. And the other interest has been in the evaporites. So in 1974, the deep sea drilling project took their ship to the Red Sea. Ron Girdler and Bob Whitmarsh wrote this article. Sorry, it's my mouse. Illustrating the structure in the Red Sea. So perhaps overlying the basement, you have this big, thick body of evaporites, and then a thin layer of later sediments on top. This is where the drill ship worked. They hypothesized that at the end of the Miocene, the evaporites are actually quite young. They were deposited till right at the end of the Miocene, which is only 5.3 million years ago. Since then, with plate tectonics, the whole region has been spreading apart, and that's created a depression. And as it's continued to spread, we've had the evaporites flowing inwards as they've lost their lateral constraint. Their ideas were interesting, but we now think there are other forces working on the evaporites to produce the flowage. This is kind of giving away some of our thoughts a bit early, but just to illustrate this, we think we have oceanic crust underneath the central Red Sea, but possibly stretched continental crust towards the coast. Because the lithosphere is much thinner underneath the ridge axis, this means that the temperature gradient across the lithosphere is high here. It means there's very fast heat loss. That means the subsidence rate near the axis will be much larger than it is towards the coast. So the result will be that the whole of the evaporites are likely to get tilted by this process. As this area subsides faster than this area, the evaporites are getting tilted, and that will also produce this, enhance this flowage. You might think a mid-ocean ridge will block evaporites. It will stop them flowing further into the basin. Well, that may be true to some extent, but there's also this effect of subsidence. It will cause tilting of the basin, and so this I imagine is an interest in other margins as well, like the South Atlantic margins. So the Red Sea has been thought of as an analogue for other salt basins. So Brazil, Angola, the areas of the North Atlantic have a lot of salt, and also the Gulf of Mexico. So perhaps it is a useful analogue. Well, that was an original thought, and I have to say I don't know the geology of Brazil too well. So what I'm going to say, I'm sure other people in the audience will know much better than me. So I'll be careful, try to be careful what I say. I've just said that in the Red Sea we have deposition of the evaporites both on continental crust and on oceanic crust. Well, I've just picked out a paper by Ian Davison where he looked at a lot of deep seismic lines, and he's mapped out the evaporites, or the salt, as all lying under stretched continental crust and none of it on the oceanic crust. So I don't know how true this is, but it would suggest that this is different from the Red Sea. So the Red Sea differs in quite a number of respects from the South Atlantic. So we have a very ultra slow spreading rift in the Red Sea. Evaporites were deposited over a longer period. I believe in the Santos Basin they were deposited fairly quickly. They were deposited onto both extended continental crust and oceanic crust. The evaporites in the Red Sea comprise a fair bit of anhydrite and shale, so they're not pure halite. I think quite a large body of it is pure halite, but near the surface we have a lot of laminated anhydrite and shale as well as halite. So it's for a variety of reasons, it's not going to be a perfect analogue for the South Atlantic. And I think it's a mistake to try to use it as an exact laboratory example of the South Atlantic. But nevertheless, I think by looking at the Red Sea, we can try to see processes occurring in the very recent past and use them as ideas for things to go and look at the Brazil margin and these other salt margins. So the reason why you might want to look at the Red Sea, the Brazil margin, the areas of the stratigraphy that would be of interest if we wanted to know what happened early on, they're very deep, they're difficult to image with seismic methods, and the stratigraphy down here, of course, is all distorted by the diapirs. They've moved a lot of things around. Dating the stratigraphy down here is very difficult. This is less of a problem in the Red Sea in that things just happen to be much younger. Nevertheless, Davison says things like diapirs started to grow during salt deposition. This is something we see in the Red Sea as well. We see evidence that the evaporites were mobile as they were being deposited, and we see evidence, he says that he sees evidence of downslope salt drainage. So this is something we see as well in the Red Sea. So it's not a perfect analogue, but there are things going on that may be similar, and it can be interesting to look at the two together. So I think I'll give credit to Enrico Bonatti and Marco Ligi for their view of the Central Red Sea. It differs from ours, but there are some valid aspects to it as well. And these are both good friends of mine, so this is not a personal criticism. We've sailed together and enjoyed our company a lot. If you look at magnetic anomalies, if you look at magnetic anomalies in the Red Sea, we see very high amplitude magnetic anomalies in certain places where you have the basalts exposed. So clearly, we think there is oceanic crust here. But off-axis, the magnetic anomalies are much more subdued. It's not clear. It's very difficult to see in this image. This is from Nico Augustin's work. Very difficult to see seafloor spreading anomalies. So I think that has been what has guided their view that, in fact, in the central Red Sea, this is their view. This is a cross-section running down the center of the Red Sea. They view it as containing a lot of stretched continental crust and seafloor spreading just starting at some of these deeps. Nereus is one of these deeps that is floored with basaltic crust. Thetis Deep is another new area of seafloor spreading in their view. So I think this could be a valid comment, but I'll come back to the magnetic anomalies later and try to explain why we may have low amplitudes here, and there's a good reason for it. So I'm going to show a few pieces of evidence that I think support the idea that it's oceanic crust and not continental crust. And actually, this is just a normal, ultra slow spreading ridge underneath the evaporites. So, for example, here I'm showing in the Red Sea, I'm showing free air gravity anomalies produced by David Sandwell from satellite altimetry measurements. I've got the sun shining from the northwest. And what you see here are these ridges that run across the Red Sea, roughly parallel to the plate motion. If you remember, the plate motion is like this. They're slightly curved. Some of them are much larger. This is actually a combined plot of topography on land. So I'm trying to show that you actually have some features that align. So the valleys on land that align with some of these fracture zones and ridges underneath the salt. But anyway, this pattern is quite similar to what we see at slow spreading mid-ocean ridges or ultra slow spreading mid-ocean ridges. This is the Southwest Indian Ridge. In topography, the warmer colors are higher topography and purple is deep. This is the ridge axis, which is a valley here in this part of the Southwest Indian Ridge. And you see these ridges that run off axis. And they also form this very, very widely spread V shape. You see this? It kind of looks like this. So here the V shape's pointing in this direction, and here it's kind of pointing in this direction. So superficially, it's actually quite similar. When looked at this a bit further, what we wanted to know is whether the gravity anomalies are consistent with this being oceanic. So what Wen has done is sampled the gravity anomalies along these lines, and he's inverted them for basement rugosity. So just using the Bouguer slab formula, invert the equation to derive the RMS variation in the basement topography. And that's what I'm showing here, his estimates of RMS basement topography across those ridges and valleys. In the red, if we assume a density structure of oceanic crust, the values are actually quite similar to what we find at the Mid-Atlantic Ridge. So Wen has just sampled the bathymetry. There's no sediment on the Mid-Atlantic Ridge, or very little. So we can compare the bathymetry, and they seem quite similar. This isn't proof that it's oceanic crust, but it says it's not inconsistent, at least. And we got access. I made contact with Zeldin, who is a Sudanese scientist, a senior scientist, who for his PhD studied deep seismic data along these lines, and he interpreted the basement and other reflections. And what Wen has done is digitized the basement reflection, shown by the red here, for this series of lines, and also the top of the Evaporites, which is in the turquoise, the light blue, and the seabed, which is, I guess, in the black, or the no, in the green. So what this reveals, he's converted them from two-way time into depth, is that there is a simple ridge underlying the axis of the Red Sea. Although in the bathymetry you see this valley, in reality the basement structure is one of a ridge. And I don't know of any active rifts where you have a basement ridge underneath the rift. But this is quite typical of an oceanic ridge near to a hotspot. You see this structure. So in the next image, what Wen has done is sampled the bathymetry across the Reykjanes Ridge. This is Iceland, which is a mantle hotspot or plume, depending on your point of view. And the Mid-Atlantic Ridge, as it runs near Iceland, the Reykjanes Ridge, forms a high. These are profiles across the ridge, and the basement underneath the Red Sea appears somewhat similar to the Reykjanes Ridge. It's more rugged, and that may be because we have a much slower spreading rate than the Reykjanes Ridge. But otherwise, it looks like a mid-ocean ridge. And Wen's found that if you plot the basement depths along with Bugge anomalies we calculate to remove the effect of the seabed density contrast. So we use bathymetry, and we use quite a low density for the seabed, only 2.2 grams per cubic centimeters. That's because the sediments have quite low density. If we do that, remove the seabed effect from the gravity, free air gravity data, you see there's an extremely good correlation between Bugge anomalies and the basement depth. Quite extraordinary. It breaks down going towards the coast quite often. So, for example, here the basement is coming up, but the Bugge anomalies are flat. You see that to some extent. Well, actually, you can't see that in the data there. But that seems to be a feature. The Bugge anomalies are relatively flat near the coast, whereas the basement can rise up. That appears to indicate there's a different density structure near the coast, which suggests that there's a lower density. And so we think this is stretched oceanic crust. But around the axis, we have this remarkable correlation. It applies quite a low density contrast of only 400 kilograms per cubic meter. This is quite low if you thought the oceanic crust comprises mostly a gabbro contrasting with halite. You'd expect a higher density contrast. So we suspect that this correlation is not just due to the basement. It's actually the crust varies in thickness, and there's probably a temperature effect in the mantle as well. So it's not just these. So we think the crust is thicker under here, probably. Just to add a little bit of geochemistry, sodium 8, these are measurements of sodium oxide in axial lavas corrected for fractional crystallization. People like Emily Klein have shown that you can use these to evaluate how much melting has occurred underneath the ridge and crustal thickness. So for the values from the Red Sea, we find the crustal thickness should be only about 5 to 10 kilometers. So it's not particularly thick, it's only modestly thick, apparently. Wen has also looked at the rugosity of basement in the lines crossing the ridge. You see this up and down variation in the basement reflection. And Wen's tried to characterize this, it's difficult because the RMS variation is occurring over a similar kind of overlapping scale with the ridge itself, with the topography of the ridge. But anyway, with his values, we find the rugosity is kind of comparable with other ultra slow spreading ridges. So again, that's not diagnostic, but it's saying that things seem to be consistent. So I'd like to come back to the magnetic anomalies. Ian Stewart shared this really nice map of the aeromagnetic anomalies. He's reduced them to the pole, so there's no inclination and declination effect. And you can see he's enhanced the color scheme. So yes, you do see these high axial anomalies, but you also, your eye's drawn to these other parallel anomalies on either side of the ridge. You can see, if you look carefully, you can see paired anomalies. So this is what we expect with seafloor spreading. You'd expect anomalies to be produced at the ridge axis split, and as the crust, new crust is formed, they spread apart. So there is some evidence, or you could say there are features that are easily interpreted as seafloor spreading anomalies. Whether they extend into the coast is another matter, and we're not so sure. As we say, the gravity anomalies show a different structure. There's also a deep seismic experiment carried out by a German group in here, which shows thickened continental crust. So it appears there is a transition going from the Sudanese coast here into the axis. So the seismic data appear to reinforce our view. So now I'd like to introduce something that Oki has done. He has taken those aeromagnetic anomalies and he's inverted them for magnetization at the depth of the basement. So he's formed a grid of the basement depths, and he's inverted the magnetic anomalies down to this level, assuming a 500-meter thick layer. And when you do that, these are these same cross sections. These are magnetizations in amperes per meter for this layer. You do see a high axial magnetization, but the off-axis magnetizations are also quite significant. So this appears to say that these subdued magnetic anomalies in the Red Sea are simply subdued because the basement is very deep. So it's just simply a depth to source effect. Just to highlight also, this pair of anomalies we think is Chron 5. So this is about 10 million years. So we think we can map the start of seafloor spreading at about 10 million years. And this magnetization peak coincides with this trough in the basement. This is where we see this transition from Bouguer anomalies not correlating with basement to where they do correlate with basement. And the same in here, you see this peak here corresponds with this feature, for example. Oki has measured the peak to trough, peak to peak amplitudes in here. If you measure the peak to peak amplitude variation, that removes some of the longer wavelength effects, which we're not interested in. And he's plotted those values against seafloor crustal age. Those results are shown by these open circles. And you see the axial anomalies have a lot of variability, but generally high values, and they decay with, appear to decay with crustal age. And surprisingly, the variation is very similar to this compilation from Kim Clickord and others in 1975. They were using deep toe data from various ridges and looking at this decay. And it looks very similar. In oceanic crust, this occurs because of alteration, weathering of the basalts on the seabed. As the titanomagnetite gets affected by the weathering, the remnant magnetization decreases. We don't necessarily, this could be just a coincidence that we see the same thing here. So it may not be the same process that we're seeing. If we're right and the actually at the end of the Miocene, the evaporites covered the ridge, while you wouldn't have had, maybe you wouldn't have had eruption at the seabed. Instead, you would have had intrusions such as formation of dikes and sills. So maybe this low magnetization has a different origin. We're not sure about that yet. If we did have intrusion of sills in this earlier stage, that may explain why the boundaries of the magnetizations vary quite a bit. Some areas there's quite a sharp change in magnetization. Other areas there's quite a smooth change in magnetization. So I'd now like to move on to look at the evaporites, and I hope you find this interesting, because you see quite a lot in the seismic data of Brazil, but you probably won't have seen anything quite like that, like we find in the Red Sea. The evaporites have been drilled, as I've mentioned earlier, at these two or three DSDP sites, and what they found when they drilled was a series of layers of halite, anhydrite, and shale. So it's laminated where they drilled, but deeper down it appears to be more massive halite. The superficial sediments on top of the evaporites are quite low density where they've been measured from the DSDP samples. They're lower density than pure halite. So that means that diaparism is not promoted in these pelagic areas. These are away from the coast. At the coast, we do see diaparism, but in these deep water areas, we don't see so much diaparism. So that means that the pelagic sediments flow on top of the evaporites quite passively. And this is what we find on the Urania cruise that this was led by Marco and Enrico. I joined. I had the job of processing the multi-beam data, and we covered one of the big deeps, Thetis Deep. And this is a 3D view of the multi-beam data we collected. And you can see in here this kind of rugged morphology. This is a normal piece of mid-ocean ridge. You see these cones, and you see these escarpments. These are fault line escarpments. Here you can see another nice escarpment, another one. And you can see these peaks coming up the side of the valley. And then you see this wonderful flows of the evaporites. The evaporites appear to be held back where the basement is high, and they're flowing through gaps between those basement highs into the valley floor. And then the evaporites are forming these kind of rounded front flows, very much like other kinds of viscous flows. If you look at RR lava flows, they also have this kind of rounded morphology. In the north, on the other hand, here, we see all these ridges. It looks like what's happened here is the evaporites have flown all the way in from the east side, and they've also flown in from the west side, and the two have merged in the center. And where they've met, we have this series of buckle folds. This is called an intertrough zone. So this will be the trough, and this will be the intertrough. And so the intertrough zones have been known to be floored with evaporites. And it now appears that this is how they've become floored with evaporites, by them flowing in from the two sides. So to try to study the dynamics of these things further, what I've done here is collect data on the depth of the top of the evaporites from shallow seismic data. So what's called this S reflection is a very prominent reflection that occurs on the top of the evaporites. So mapping that out, you see, okay, so where it's gray in the center here, this means either that there's basalt exposed, or maybe there's some missing data. Here's missing data. But where you see these symbols, these are the deeps. And you can see that where the evaporites have flown in and covered the axis, the side is depressed. There's this kind of like big depression at the side. And so what's happened is evaporites have flown in, but as they've flown in, there's been this depression, like, I suppose, like a giant slump. You might think of this as a bit like a giant slump, although it's probably flowing in a more viscous way. If you look at the Bouguer gravity anomalies, as I've said, these correlate very strongly with the depths to basement. So you can interpret this as like a giant valley that runs across the ridge. And you'll notice that the flowage appears to have occurred where the valley is. The deep occurs where the basement is actually high. Come up here again. Here the basement is deep. There's this big deep valley. This is where the evaporites have flown in. Here the topography is deep, but the basement is high. So this kind of inverse correlation. And in here, where you have another big valley that crosses the Red Sea, this is where the evaporites have flown in, and you also have these deflation areas to the side. So actually, this is really neat, I think. It shows there's a connection between the geodynamics, if you like, that have created an ultra-slow spreading ridge with a typical ultra-slow spreading ridge morphology underneath the evaporites, and that has affected the flow of the evaporites into the axis, or stopped it in places. And ultimately the pattern we see, and if you look at a Google Earth map of the Red Sea, you'll see these big deeps. This pattern of deeps and then high areas between the deeps is ultimately due to this whole process. It's a really neat combination of geodynamics and basement morphology and the flow of the evaporites. There's a remaining question that I've struggled with and haven't really come to any solution. If the we know that, let me say, Iranian Namakias, these are salt flows. They flow very fast. Chris Talbot measured, they can flow fast. Chris Talbot measured rates of 1 to 8 meters per year for one particular Namakia, and it occurred only in the 2 months of the wet season. So when it rained, then we got this movement. They move fast because of pressure solution creep. Apparently you only need very tiny amounts of trace water around halite crystals for them to deform quite fast. Now, the evaporites in the Red Sea were deposited underwater. They surely, and they have sediments underneath them, they surely must have trace amounts of water. So it's unclear why they aren't moving faster. They appear to be only moving at plate tectonic rates. If they were moving fast like water, you'd expect them to have flooded the entire axis. That hasn't happened. So the question is, why is that? And maybe the answer is the lamination. We have a lot of anhydrite and shale. When we look at seismic data of the evaporites, we see a lot of lamination in high resolution seismic data, at least in the top of the evaporites. Maybe that makes the evaporites more rigid and viscous, effectively viscous, than you might expect from pure halite. So I'd now like to show a couple of seismic lines, one here near the coast of Sudan and another one from nearer the coast of towards Saudi Arabia. They show some interesting differences. The one in the north near Saudi Arabia, you can see this wonderful pattern of lamination within the evaporites, and you can see growth structures. So here, for example, the dip of this reflection is quite different from the dip of this reflection. So this is evidence that the evaporites were deforming as they were being deposited. But what's interesting to me is that there's an unconformity here. You see this reflection come up and stop. Here's another one that's truncated. There's an erosional surface here. On the other hand, you can look at other seismic data. These are extremely old data collected in 1965, when the Robert Conrad did a leg through the Red Sea. They're rather old, but I think they're actually really good for considering their age. They only use a 25 cubic inch air gun, and I think this is the credit to people like John Ewing at Lamont when they were developing the seismic method, that they produced data like this. But anyway, we see on the top of the evaporites here, there's no evidence of an erosion surface. And the same here, there's no clear evidence of an erosion surface. You notice that the two-way time for this point is less than the two-way time for this point. Can look at that further. Depth converted those 2 points. So this is the point in the north, which has an unconformity. This is the point in the further south off Sudan, which doesn't have an unconformity. Well, this is curious, because if the unconformity was produced by drawdown of the Red Sea in wave erosion or effects of rainwater, if you have a continuous salt surface, how is it possible that this has been affected but not this? It's the wrong way around. I think the answer, we checked that this isn't just due to isostatic effects. So that's what these curves are about. But the main reason for this is that this area was more greatly affected by flowage of the evaporites and deflation of the evaporite surface. So I think mapping out unconformities actually could be, and non-unconformities could actually be quite useful to working out the dynamics of the evaporites, and maybe in other situations as well. So recently I've got interested in trying to reconstruct the level of the evaporites at the end of the Miocene. So the present day, I've averaged all of the data that WEN has digitized, and the evaporites appear to lie at 908 meters beneath sea level, present day global sea level. What I've done here is to try to apply a series of corrections to see if we can estimate the depth of the evaporites right at the end of the Miocene. This is the result of correcting for thermal subsidence of the lithosphere underneath the area, and also loading by water overlying the evaporites and the Pleistocene sediments. So you notice this isn't to scale, it's just schematic. I've then applied another correction to allow for the overflowage of the evaporites onto younger oceanic crust. So we know the evaporites are 5.3 million years, and we know the crust here is about 5.3 million years. So all of this material in grey must have come from in here out onto the younger crust. So what I've done next is taken this and put it back on here and allowed for isostasy. So that moves the evaporite surface up to 76 meters beneath sea level. And then I've applied a further correction for pore water diffusion loss. So somebody has modeled pore water salinity profiles and using their results, along with some results on the loss of sodium chloride through diffusion in brine lakes. Combine those, we end up with this level for the evaporite surface at the end of the Miocene, which is remarkably close to modern sea level, and it's close to the Miocene estimates of Miocene sea level. There are different estimates, but they suggest that it was around this level and maybe fluctuated somewhat. So this is interesting. It suggests that when we see this unconformity, it may have occurred when either during one of the drawdowns in the late Miocene, so when sea level dropped, according to some models below this level, or it may have occurred when the Mediterranean dried out, because the salt that forms the Red Sea is believed to have come from the Mediterranean, and the Mediterranean dried out in the late Miocene in the so-called Messinian salinity crisis. So I think that's interesting, and it's in peer review at the moment. So I hope the reviewers treat us kindly. So finally, the last topic of the talk, I'd like to come to discuss the seismicity of the Red Sea, and this also is linked to evaporites. They seem to connect a lot of these different aspects. This is a map of earthquakes in the Red Sea. The red symbols are represent body wave magnitudes derived from the ISC. And you'll see in the south, it looks fairly typical. You have a lot of earthquakes. This is typical for an ultra slow spreading ridge. You'll see clusters of earthquakes like this. But the north is pretty barren. There's very few earthquakes running from about here all the way up to the southern Gulf of Suez and the Aqaba transform fault. So between here and here, there's very little seismicity. There have been a few people have noticed this and also written about it.
Neil?
Yeah?
Neil, can you hear me?
Yes.
Yeah, I think your screen froze.
Oh, is it frozen? Can you see my cursor?
You froze, and your presentations froze on the last slide, reconstructing evaporite surface.
Okay.
Try to.
Okay, I'll stop sharing and I'll come back.
Yeah. Yeah.
Okay. Right, I'll try again. I think my image is frozen there.
Yeah. Your image is frozen.
Okay. Let me try and share again. Let's see if you can see it. It's not letting me share. Okay. Let me perhaps come out of this then. I'll try this differently. Is that
what
okay?
About, let's see. Yes. No.
Okay, I'll just leave it in that. Sorry. Yes. Say that again. The Northern Red Sea has very little seismicity, and this could be worrying. Does it mean that we have a gap with seismic potential? If all the missing seismic moment were released in one earthquake, it would be quite a large event. It would be like a magnitude 7 event in the Red Sea. It would be an enormous earthquake, and obviously that's would be a huge concern. We don't think that's the case, because people who have studied the historical documents going back 2,000 years or so that the Arab peoples around the Red Sea have kept, there's no evidence of there being a big earthquake in this part of the Red Sea. So we think it's not a gap with seismic potential. If that's the case, then what can explain it? Well, one thought is that it's the result of thermal blanketing by the sediments overlying the crust here. They keep the crust warmer than otherwise. So here's a line of heat probe measurements collected by Jim Cochran, and in this paper by Fernando Martinez and Jim Cochran, they modeled the heat flow here, and they predict that the top of the basement is about 100 degrees C warmer than it would be otherwise. So it seems that the basement is likely warmer than you would expect for normal oceanic crust, and that will tend to thin the seismogenic layer. Another possibility is that the evaporites produce overpressures. Fluid that's compacted will have a hard time escaping to the evaporites, which have low permeability. So you end up with high overpressures. And of course, overpressures, if you get them in you know about fracking experiments, they can drive fracturing. Well, that's true over a short term, but over long term, they should lower the strength of the material. So this might be another explanation, although we don't like it particularly well, because high overpressures would lead to weakness in the evaporites, and they should be flowing into the axis faster. So that's inconsistent. So we don't think that's a good explanation. Thermal blanketing seems to be the most likely explanation. Another view of this seismic gap. So you can see magnitude against distance, and you see this very striking lack of seismicity in the northern Red Sea. Here's a similar plot for the Southwest Indian Ridge, showing earthquake magnitudes in the red, and in the purple I'm showing seismic moment values. And this is what a normal mid-ocean ridge should look like, ultra-slow spreading ridge. And that's what the southern Red Sea does look like, but not the northern Red Sea. And we know the separation rate of the Red Sea, so we can work out this thing called coupling coefficient, which is a measure of how much of the plate separation is occurring by slip-on faults during the earthquakes. And you see there's this factor of 10 difference between the north and the south. Quite a dramatic difference between the two. In here, you see earthquakes all the way along, but what I've done is binned the moments of each earthquake, worked out a cumulative moment within each parcel of seabed. And you see from the color change in the north, it's actually much lower than it is in the south in the reds. You also see this clustering. So Mojave Mons, for example, is a known volcano. It's been mapped with multibeam lying in here. It seems some of the seismicity may be associated with volcanoes. So we have earthquake data from the Saudi Geological Survey. They donated some of their data to the ISC. It's not complete, so we've had to make an adjustment for incompleteness. But when you do that, you find that the magnitude frequency diagram, here we're using incremental frequencies, it's steeper than you would expect for tectonic earthquakes. It's about 1.22, so it suggests that some of the earthquakes here are occurring in volcanic swarms, which I think is interesting. And so we're trying to continue this work. I went to sea 2 years ago now with Nico Augustin from GEOMAR in Germany. He led this cruise, and it was funded by the German government ultimately. And we went on the Dutch research vessel, the Palakia, and we had a group of Sudanese young scientists with us. And this is Eldin persuaded him to come and join us, and really enjoyed talking with him about the geology of the Red Sea. Very capable scientist. And here's some of the data. You see these wonderful patterns of volcanic cones, some with collapse pits inside. You see these domes, which may be sills, shallow sills, or they could be lava domes. And then around the edges, you see this wonderful pattern of flowage of the evaporites, and it's very complex. You see in the shading, you can see where the flows have gone across underlying basement ridges. So here's likely to be a normal fault, another normal fault here. You see this feature, big crater. Nico suggests this is possibly due to eruption underneath the evaporites, and eruption caused dissolution of the halite component, and you end up with a crater. So there's a lot to interpret. So that's So here's a summary. So we see this, I mean, the big main point is that we see this interesting connection between the crust in the central Red Sea, which is hidden from us, but the gravity anomalies with these wonderful data produced from satellite altimetry measurements is revealing the basement structure underneath the evaporites. And it's showing us a typical ultra slow spreading ridge. And the rugosity of that ridge is affecting the flow of the evaporites. And the flow of the evaporites is dictating the shape of the seabed and ultimately the geomorphology. So there's this wonderful connection between these different elements. And perhaps the evaporites are also affecting the seismicity through this thermal blanketing effect. So that's it. Thank you very much for listening, and I'll be glad to answer some questions. Unfortunately, my figure has frozen, but I can answer hopefully.
Thank you, Neil. You can try to stop your can and start again, see if it's working.
Okay.
Now start again.
Okay.
No, it's frozen.
Okay.
Okay, but at least we hear your voice. So thank you so much, Neil, for your talk. It was a very interesting topic. So now we are open for questions from our audience, and we already have one from Marcelo. Marcelo Silva asked, does the Red Sea have the potential for exploring polymetallic nodules, or is it only associated to more spread oceanic crusts?
There has actually been a lot of interest in the Red Sea. It turns out there are massive sulfides in the Red Sea, but they're produced in a slightly different way because you have these hot springs formed underneath the brine. Somehow the brine leads to the exhaled particles forming a mud. So at Atlantis 2 Deep, for example, there's a large body of mud that has a high metallic content, and there have been companies and the Saudi government and other governments interested in exploiting those minerals. And because it's a mud, it may be easier to remove by suction than hard rock. It's of course controversial as well because it would have big environmental implications as well. So there are two sides to the story, of course.
Okay.
Yeah.
Aderson Nascimento, which is a colleague from the Geophysics department, he's asking, he's first said, we're talking, and he's asking, do you have any focal mechanism or moment tensor data from the seismic events? If yes, what they show?
There are events. I mean, I've not analyzed them myself, but there are centroid moment tensor solutions in the Red Sea, and they show more or less what you expect: normal fault mechanisms and some strike slip, mostly normal fault mechanisms down the center of the Red Sea. I don't think they show anything particularly unusual. I think they're just normal mid-ocean ridge events.
All right. Do we have more questions? You can ask people. Don't be shy.
No. I think...
mais perguntas, pessoal. Pode perguntar. Não fiquem com vergonha. Oh, also, Julia Guerra is saying, thank you, amazing talk.
Aderson do Nascimento is great talk.
Yeah. So, well, people is a bit shy today, I don't know. So, if you guys don't have any more questions, well, I would like to say again, thank you so much, Neil, for your presentation, and I hope you enjoyed. And a lot of people asked me because of the hour, it's 2 p.m. here, many people won't be able to be here to watch you, but they are saying they're going to watch you later. And we hope you can give us more talks in the future. And that's it. Thank you so much.
Well,
hope you enjoy it. Okay. So
I would like also Neil for your presentation.
Okay, thank you very much. Yeah.
Yeah, thank you.
Yeah, that's it. And it's a pity your camera is frozen right now.
Yeah.
But that's fine.
Okay.
Okay, so we're finishing. Oh, okay. Aderson has another question.
Yeah.
What about the? Okay, go on.
Others, what about the focal depths of their normal events?
Well, I think they're fairly shallow. They're mid-ocean ridge events, and I don't think they're very well determined. So I haven't tried to make anything of the depths really. They're normal shallow events that you get at mid-ocean ridges, and they're not particularly accurately determined. From the point of view of the Saudi array is really good, Saudi seismometer array, but because the Red Sea is outside the array, the depths aren't very well determined either. So they're only really determined from the centroid moment tensor solutions. And I don't think they're particularly unusual. I've not put in much effort to understand them. They're fairly normal, I think.
That's all. Say thanks.
Okay, so another questions, people. Okay, so the talk was, we're finished our talk here with Neil, and if you guys have another questions, you can for Neil, you can say, you can share your email or something.
Yeah, it's I don't know how I share it. It's neil.mitchell@manchester.ac.uk. So yeah, if you Google Neil Mitchell Manchester University, I come up quite easily. So yeah, please just send me an email and I'll try to answer it. Yeah.
Yeah. All right. Thank you, Neil. We're finishing here.
Okay.
Bye-bye.
Bye-bye. Thank you very much. Bye.
Thank you.
Bye.